Hi students, I'd like to walk through this example problem. This is an example problem for the calculating the maximum, minimum, mean, and alternating tensile stresses. So in this section, we're going to talk about, you know, fluctuating stresses, and that's a state of stress that changes with time, and what its effects are. So what we need to do is we need to look at, we have equations for what the mean, if we know what the minimum and the maximum stress is in the situation, we can calculate the mean stress, the alternating stress, and the stress ratio. So essentially that's what we're doing with this problem. We're going to calculate the minimum and maximum stresses. In this case, this is a cantilevered beam. I showed you another video in this section where we calculated the bending moments, so you can find the maximum bending moment where we're going to find the maximum stress. So the other way to do it would be with a shear and bending moment diagram, but you need to be flexible about how you find these stresses. So in this case, I want to show you an example of using deflections in beams to determine what the stress is. So it's just one method of determining what the maximum stress is. Again, we did a shear bending moment diagram in the other movie, and that's how we can find the maximum stress in that situation. But in this situation, it's a little bit different. So we're going to use beam deflections to find out what the stress is. Okay, so a little bit about the problem here. What we have is a flat spring. This little thin piece here, that's our flat spring. It's going to essentially be a beam. And that beam is loaded by this cam and cam follower. Okay, so what we have, this is a single ball ejection system. And as the cam goes around, the follower here goes back and forth. And then this beam here, it's a little spring steel beam, it's going to be loaded by the cam follower, where actually it does loading of the cam follower. It keeps the cam follower up against the cam. Okay, so here we have okay, so it's going to be loaded at all times, and when it's at its maximum deflection here, this Y max 8 millimeters, that's going to be the maximum loads, and when it's at its min deflection, that's going to be the minimum load. So we're going to have to calculate the maximum and the minimum stresses based on these maximum and minimum deflections using our beam formulas. Okay, so first of all, what we do is we got to write our givens and our finds. We're going to given a steel spring. It's a cantilever setup. The length of the beam here is 65 millimeters. The thickness would be this T, 8.8 millimeters, and then B is the width across. That's this B. That's 6 millimeters. Y is our maximum deflection. So Y max is this 8 millimeters, and Y min is the 3 millimeters. And what we are to find is the maximum stress, the minimum stress, the mean stress, the alternating stress, and then the stress ratio. So we're going to be calculating our stress theta from the bending stress formula, sigma equals mc over I. And to do that, what we're going to do is we have a relationship between load and deflection that we can actually get from Appendix A14. Okay, so Appendix A14 talks about a cantilever here. This is a cantilever beam. So these are beam deflection formulas in the back of your textbook. And table A14.2 is the exact beam that we're talking about here. So at the end is where we're going to find our maximum deflection, okay, at the point of the load. And then, we have a formula here for calculating the deflection at any point along the beam, but we're only concerned about this one right here. So we have this deflection where Y equals P times L cubed over 3EI. Don't get too hung up on the negative sign here, because really the load, and because essentially it's just the way the problem's set up, it's negative, but I'm going to leave it as if it's not negative here. It's just a Y deflection. Okay, so what I did with that is I solved this for P. Okay, so now we have a relationship between what our deflection is and what our load is. Okay, and from that we can calculate what our min and max loads are based on our min and max deflections. Pretty neat, huh? So we have to find I, and I for a rectangle is bh cubed over 12. I solved that for 0.256 millimeters to the fourth, and our E is 207 gigapascals. Again, page 788, bottom, small type. Okay, so E equals 207 times 10 to the third megapascals, which is newtons per millimeter squared. Our sigma max is going to be based on our max deflection, right? Okay, so our P is going to be, what I'm doing is I've solved, I input all the variables for my equation. That's this equation right here, 3EIY over L cubed. And I solved that with all my units, and what I get is a P is 4.63 newtons. Then we know that our moment is going to be P times L, which is 301 newtons per millimeter squared, and then our MC over I is going to be 470 megapascals. Now we got our max now. Now we have to find our min. Our min is going to become the same methodology, but we're going to be using the minimum deflection of 3 millimeters right here. So enter into this same, the moment is the load times the length, which is 113 newtons millimeters. Therefore our stress, MC over I, equals 176 newtons per millimeter squared, and that equals 176 megapascals. So now we have our mins and maxes. Okay, and what you need to understand with this one, this is a particular arrangement. I'm going to give you a different example in your textbook for your assignment for lesson 3. So your lesson 3 assignment is going to be a little bit different arrangement, but it's going to kind of use the same methodology where we're finding load from deflection. Now, if you've seen something on the test like this, it could be a beam bending problem. It could be any other kind of problem where the stress is fluctuating. And really what we need to do is to use what we've known to calculate our maximum and minimum stresses. And then the new stuff here would be the mean, the alternating stresses, and the stress ratio. So let's finish this problem up. Okay, so therefore our mean stress is the max stress plus the min stress divided by 2. That's equation 5.1. And so our mean stress is 323 megapascals. Our alternating stress is sigma max minus sigma min divided by 2. That's equation 5.2. And therefore our alternating stress is 147 megapascals. Then our stress ratio is going to be the min divided by the max. That's equation 5.3, and that is 0.37. Since the spring is always in a state of positive stress, this is called a fluctuating stress. You'll see that from figure 5.4, and here's what it would look like. So you have a stress ratio that's somewhere between 1 and 0, which means that if we plot our stress versus time, we have a stress that fluctuates between a minimum positive stress and a maximum positive stress. It's all positive because it's above this 0 here. Okay, so this is the example of how to calculate the alternating stress, the mean, alternating, and stress ratio in a beam that is subject to cyclical loading. Thank you.